Hello friends, I'm Arvind Nizami and today we are going to have the derivation for the displacement fields of Euler-Bernoulli beam using its assumptions. Okay, so how we find the displacement field, we'll see. So hence in this slide itself it is shown the displacement field of the Euler-Bernoulli beam. So how we will get this displacement field, we will see. So let's start. So we know that if we want to get the displacement field, so our objective is to get the displacement fields of the Euler-Bernoulli beam, of Euler-Bernoulli beam. Okay, so from the Taylor series expansions, what we know that any displacement fields, either the in-plane displacements, let us say u of s comma z, how we can write? We can write it in short, I equals to 0 to nth polynomial order u of I, z of I. Yes, this means we can write it like u naught, which is a function of x, into z to the power 0, that would be 1. So u naught x plus u1 of x into z1, that is z, plus u2 of x into z square plus u3 of x plus z into z cube plus so on up to un of x into z to the power n. Okay. Similarly, the transverse displacement w of x comma z, that can also be written as what? I equals to 0 to n wi z of I. Okay, so now we just put w naught into z to the power 0 is 1, so w naught of x plus w1 into z to the power 1 plus w2 z square plus w3 of x, or is the function of x here, okay, into z to the power cube plus so on up to wn of x z to the power n. Okay, so this is what we can write the displacement field using the Taylor series expansion. Taylor series expansion. Okay, so up to the nth order. But what Euler-Bernoulli states, we will see the assumptions and then we will see how this displacement field will get reduced. Okay, and this will reduced and finally we will get this displacement fields. Okay, so why the assumptions are applied for the Euler-Bernoulli? So assumptions. Assumptions for Euler-Bernoulli beam. Bernoulli beam. Okay, this is also called the thin beam theory. Okay, thin beam theory. Euler-Bernoulli beam is also called thin beam theory or pure bending theory. Okay, or pure bending theory, because there is no shear taken into account. Okay, so it's also the pure bending theory. This is valid for the very thin beam. Okay, so that is the assumptions. So the first assumption is what we write. If our beam is there, let us say, sorry for my drawing, that I am not having a good drawing, so let us make it anyhow. Okay, so this is our beam. Okay, and if we say the transverse fiber, okay, so transverse fiber means what? We are talking about this fiber, vertical. Okay, so the fiber, the first assumption is the fiber, that means here transverse fiber, okay, fiber is infinitely rigid in vertical direction vertical direction. Okay, or the transverse already I have written, so the transverse fiber is infinitely rigid, you can say. Okay, or in other words, it also states that no stretching is allowed. This means what it means? This assumption means no stretching is allowed along the transverse direction. So what is the transverse direction? Let us give some axis coordinates. So if you say the mid, it is the x, and the vertical transverse direction, it is z axis. Okay, so x and z, and we assume the width direction, that is the y direction, that is the width b is much less, very thin beam. Okay, so very less. So that's, we are just talking about the x and z directions. Okay, not y right now. Okay, so no stretching is allowed along z direction or the transverse direction. Okay. So what this states, if we say what this states, this states that epsilon zz, that is the stretching. Okay, so epsilon zz, that should be equals to 0, because no stretching is allowed in that direction. So along the z direction, what is the stretching? That is the strain, epsilon zz, that is called the stretching along the vertical directions or transverse fibers. Okay, so if it is 0, then what this implies? This implies that what is the strain epsilon zz? Epsilon zz is del of w of x comma z by del z. Okay, it is 0. So del upon del z of, if we put the functions of w of x comma z, okay, what we have chosen here, w of x comma z, if you remember, so w1, w naught of x plus w1 of x into z plus w2 of x into z square, okay, w3 of x into z cube, and so on. Okay, so if you put that function, so is it possible to get the 0 value? Is it possible to get that 0 value if you put that function? No. So what is the possibility here? What is the possibility here that this del w by del z means epsilon zz would be equals to, that is what we have, del of x comma z upon del z equals to 0. This implies that it is only possible when these are not present. Okay, because if the z would be present, it would never be 0. Okay, for this to be 0, strain stretching epsilon zz should be 0. This should not be there. Okay, so this implies that w of x comma z is actually a function of only x. Okay, if this is a function of only x, then the strain epsilon zz would be 0. Okay, so this is only possible when it is a function of x only. Okay, so this implies that w of x comma z is only w naught of x. The first displacement fields we got along the transverse fiber. Okay, w of x comma z equals to w of x. This is what, this is the one which we have, the displacement along the vertical directions. Okay, so any beam if we have, if it is loaded, what will happen? Basically every beam has its neutral axis, so let us make a neutral axis. Okay, and if this beam will bend, let us say this beam will bend like this. Okay, just this beam will bend like this. Okay. So the neutral fiber would also be there somewhere. Let us say let's make this neutral fiber. Okay, neutral axis of that. Now, what this w of x z? So first of all, this along x, and this vertical is the z direction. Okay, so the displacement along the transverse direction in z direction is the w. Okay, transverse displacement. So that transverse displacement, what it states, if you see w of x comma z equals to w naught of x. This is what stating at any point within that beam, okay, any coordinate of the z, okay, which is, if it is getting deflected, it would get the displacement w naught of x irrespective of the z. So the whole beam thickness, okay, the whole beam will get the same displacement of the particles along the z directions. Okay, so that's why if you see, we always see in the book, undergrad book, that the beam is always shown in a line. Okay, they always show a beam as a line member. Okay, so why they make, because this is only the neutral axis they represent this beam, because the thin beam, okay, so it is assumed that there is no stretching in the vertical direction, so each of the portion, any fibers you will take along the horizontal direction, it will bend with the same deformation. Okay, there would be no change. So therefore we assume that we can take the neutral axis and the deformation what the neutral axis is giving, so each of the fiber would give the same displacement. Okay, that is behind this. So now this is the first, we get the displacement field from these assumptions, first assumptions. Okay, now coming to the second assumptions. So let us go to assumptions 2. Assumptions 2. What is that assumption 2? That states that plane section remain plane before and after bending. Okay, so what is that? Make a fiber, make a beam, then the initial fiber is what? Let us say when it is having no deformation, let us say this one we have chosen as fiber 1 1. Okay, and when beam will get deflected, okay, so let us say the beam get deflected, I am making here, let us say the beam get deflected like this. We are not taking any horizontal force. Okay, so there is no horizontal displacement in the homogeneous and isotropic beam. Okay, so we are not considering the horizontal in this way. So now what is there? This is the neutral axis here. There would be the neutral axis also here. Okay, and this 1 1 would also bend here. So this, after bending, if you see, this remain also plane. Okay, just like this is straight, this is also remaining straight. So let me take this, and once it's bent, after that also, after bending, it is remaining plane. Okay, so what is this? In actually it was initially it was like this. Okay, and now after bending it shifted and like this, but it is remaining plane. It is not behaving like this. The fiber after bending is no more just like this or anything like higher order or quadratic variation or cubic variation, but it is remaining like a straight line. Okay, so it is remaining linear. Okay, it's linearly varying. Okay, so what it states, it states that the displacement field what we have chosen, u of x comma z in the previous slide. Okay, here we have considered u naught of x plus u1 of x into z plus u2 of x into z square and so on. So this displacement field what it is taking in plane displacements, it will no more now have any higher order term. Okay, so we will eliminate all the higher order term. Okay, and it will restrict to the linear. Okay, so it will be linearly varying. So plane sections remain plane. Okay, so u of x comma z is u naught of x plus z times u1 of x. Okay, so right now what we are concluding that there is no axial load is applied, so it would not have the rigid body movements, so it will be there only. So we are eliminating this u naught of x as 0. So finally u of x comma z is equals to z times u1 of x. Okay, now the next assumptions what we have, assumption 3. What is that assumption? That plane sections remain perpendicular to the neutral axis. Okay, so plane sections remain perpendicular to the neutral axis. What does this specify? That if the beam bends, okay, so what is happening? The plane section which was there, what we have seen that when it was a beam just like having some thickness, okay, after bending, this is the neutral axis. Okay, so the fiber of the vertical fiber after bending is also remaining perpendicular. Okay, so before bending we know it was perpendicular, the neutral axis was perpendicular to the vertical fiber. Yeah, this was the vertical fiber, and after bending also it is remaining perpendicular. So if you make a tangent at this point to this curve, to this displacement field, okay, this curve is what? Neutral axis representing the w naught of x. Yes, that is the transverse displacement is represented by this curve. So now if we take this tangent at this position, what it implies? Tangent to this position means with the x-axis, if you will find, that is the theta rotation. So what it implies there is only it is remain perpendicular. So the shear strain gamma xz equals to 0. There is no shear strain. Okay, it is purely bending. Okay, so that is what, if theta, if you find out, okay, so that is what, that is the derivative, because if you take the tangent, so tangent on what? We are taking on w naught of x, so it would be del w naught of x by del x. Okay, and it is going clockwise direction, so generally we take anti-clockwise from x-axis as positive, so it would be minus of del w by del x. So theta is equals to minus of del w naught of x by del x. Okay, now also what we can see here, if we enlarge it, so this theta in actual, let me make it, initially it was with another color, take this color. Okay, so it is bending x-axis. Okay, and here it's the theta, it's making theta angle with this. Okay, now so this is perpendicular to this, and this was initially perpendicular. Okay, so this was also b theta. Yes, because it, to make it 90 degrees, if we minus it, okay, we will get theta. Okay, so if you want to find this displacement is what? Any position at z, if you want to find this horizontal displacement, that is what? U of x comma z. Okay, in plane displacements, so this displacement is what? If you multiply, so if you take the tan of theta, this is roughly theta equals to what? P by b. Okay, so P is what? u of x comma z, okay, and b is what? Z upon z, okay. So u of x comma z finally would be z times theta equal z times theta is what? You have already found out from geometry, minus del w by del x, okay. This is what we are getting from the geometry. Now come to the mathematical derivation. Gamma xz is equals to 0. What is gamma xz? Gamma xz is del u of x comma z del u by del z plus del w by del x. So w naught of x by del x, and that should be equals to 0. Okay. So del by del z of u of x comma z. What is u of x comma z after applying the assumptions? After applying the assumptions, what you got? U of x comma z as z times u1 of x. So z times u1 of x, okay, that is equals to minus of del w naught of x by del x, okay. So if we take this, what is that? Del by del z of z times u1 of x equals to minus of del w naught of x by del x. So if we take the derivative as partial derivative with respect to z, what it will have? It would be 1. So u1 of x would be equals to minus of del w naught of x by del x, okay. So finally we will put u of x comma z would be what? U of x comma z equals to minus of, if you put in this formula, u naught of x, that is 0, plus z times u1 of x. So z times u1 of x. So it is z times u1 of x, okay. So that is z times u1 of x is minus of del w naught of x by del x, okay. So u of x comma z is finally minus z times del w naught of x by del x. Okay. It is when this, we are assuming that the load is only transverse, okay, only transverse, no axial load is applied. We are not considering any axial load, okay, no axial loading is applied. So we will get this to displacement. This is the one, and the another was the transverse displacement, which was w naught of x. Okay, thank you. So we are closing here, and in the next class, inshallah, we will see the derivation of the governing equation of the beam. Okay, thank you.